Welcome to Learning Chemistry with the Professor's DuBois. This is Professor Corey, and today we're going to learn how to calculate average atomic mass. The mass of an atom is the sum of the number of protons and neutrons in its nucleus. Atoms of the same element that have different masses are called isotopes. If you need a refresher on isotopes, search our other videos for this topic and then come back to this video. In our isotopes video, we learned that if we take a sample of carbon and measured the mass of every carbon atom, the majority of atoms would weigh 12 AMU, and a much smaller number of atoms would weigh 13 and 14 AMU. Since all carbon atoms have 6 protons, the number of neutrons must vary to account for the mass differences. If you look at carbon on your periodic table, you will notice that the mass is given as 12.0107. Atomic mass units, or AMU. You may even wonder how this number can exist if the mass of a proton is 1 AMU and the mass of a neutron is 1 AMU. Wouldn't the masses need to be whole numbers? The reason the given mass is not a whole number is because it is the average atomic mass. This becomes a complicated problem because we're used to calculating averages by summing the values and dividing by the total number. And this works for situations like exam average because each exam has an equal potential value of 100%. Or in other words, we could say each exam contributes equally to the average. The average atomic mass is different because there are not equal amounts of isotopes. For instance, if we were to look at the 3 isotopes of carbon and calculate the average mass, it would be tempting to sum the 3 masses and divide by 3, but this is incorrect. The reason this will not work is because there are many more carbon-12 atoms than carbon-13 or carbon-14. In fact, we can often predict the most common isotope for an atom by looking at the average atomic mass. Carbon's average atomic mass is 12.0107, so I can say with some certainty that the most common isotope is carbon-12 because the average atomic mass is very close to 12. Use your periodic table to answer this question. Pause the video if you need more time. The most common isotope for hydrogen is hydrogen-1, H1. This isotope is sometimes called protium. The other 2 isotopes for hydrogen are H2, deuterium, and H3, tritium. It is not expected that you memorize the isotopes for elements, and while the 2 examples used so far, carbon and hydrogen, have 3 isotopes, it is important to realize that not every element has 3 isotopes. The types of problems you will encounter in general chemistry may be conceptual, like predicting the most common isotope given the average atomic mass, or calculations to determine the average atomic mass from data about the isotopes. When you're asked to calculate the average atomic mass, the masses of the individual isotopes and their relative abundance will be given to you. Excellent question. Relative or percent abundance is the relative amount of a particular isotope expressed as a percent. Imagine you had 10 atoms of an element and 2 of the atoms weigh 10 AMU while the other 8 weigh 12 AMU. I simply made up these numbers, so let's call this element XX, and it's not an actual element. To get the percent abundance, we would take the number that weighed 10 AMU divided by the total number of atoms. This would be 2 divided by 10, which equals 0.2. To make this a percent, we simply multiply by 100. So 20% of the atoms weigh 10 AMU. If there are only 2 isotopes, like in this example, we can determine the percent abundance of the other isotope by subtracting the first from 100. So 80% of the isotopes in this example weigh 12 AMU. We could also calculate this value like we did for the 10 AMU isotope. In this case, the math would be 8 divided by 10 equals 0.8. And then we'd multiply by 100 to get 80%. So the percent abundance for XX10 is 20% and XX12 is 80%. So how do we use this to calculate the average mass for this fictitious element, XX? Realize we cannot get an average by adding 10 plus 2 and dividing by 2. The reason this will not work is because we have many more isotopes that weigh 12 AMU, so my average will be greater than 10 and less than 12, but much closer to 12. The way we calculate the average atomic mass is to sum all of the masses and divide by the total. So for our example, we could calculate the value by summing the masses of all 10 atoms. then dividing by the total number, which is 10. Our answer is 11.6. This does make sense because we know the two isotope masses are 10 and 12. And we also know that there are many more that weigh 12, so we would expect the result to be between 10 and 12 and closer to 12 than 10. Unfortunately, the method that we used above is not practical for chemistry. Even a very small sample would contain several billions of atoms. We will therefore use our percent abundance data for this calculation. Here is the formula for the calculation. For our previous example, we had two isotopes, the 10 AMU isotope and the 12 AMU isotope. We will have two terms in our formula. 20% of the isotopes are the 10 AMU variety, while 80% are the 12 AMU variety. So I will divide 20% by 100 to get 0.2. Then I will multiply by the mass of the isotope, which is 10 AMU, resulting in a value of 2. I will do this to the other isotope as well. Lastly, I will sum the two numbers, 11.6 AMU. Now I will walk through a more technical problem and provide two practice problems for you to try on your own. Let's make some observations before we start. First, notice that the masses provided are to 4 decimal places instead of whole numbers. We will use all of these numbers in our calculation. Some problems may only give the isotope symbol, like silicon-28. In that case, you can use the mass of 28 AMU. But if a more precise mass with more significant figures is given, use all of those numbers in your calculation. Another observation is that there are 3 isotopes, and with some rounding, I can put them in isotopic notation, Si28, Si29, and Si30, and from this, I can estimate that the average atomic mass will be larger than 28 and less than 30. The last observation I have made is that most of the isotopes are the Si28 isotope, so I would expect the average mass to be closer to 28 than 30. Let's set up our formula for 3 isotopes. For each isotope, divide the percent abundance by 100, and multiply this decimal by the actual mass of that particular isotope. Do this for all 3, then sum your results. The average atomic mass is 28.0854 AMU. Does this make sense? It does. We predicted the mass to be between 28 and 30, but much closer to 28. This simple check is very effective at catching calculation errors. Next is a conceptual practice problem for you to try. Pause the video if you need some time to consult your periodic table and think. The average atomic mass given on the periodic table for argon is 39.948 AMU. This is very close to 40, so we can say with some certainty that the most abundant isotope is the argon-40 isotope. This next problem will require some calculations. Pause the video and try this one on your own before I display the answer. Does your answer make sense? We know that the average will be between 69 and 71, and we know that more of the atoms are gallium-69, so we would expect the result to be closer to 69 than 71. The answer is 69.7231 AMU. Thanks for joining us. Be sure to give us a thumbs up if you liked the video, and subscribe if you would like to see more topics on learning chemistry with the Professors Du Bois.